in the unicycle model, what we have is there'll be two wheels, each having independent control, VL and VR. Now, varying VL and VR, you can navigate the bot with a particular linear velocity and angular velocity. Now, why I've stated here configuration, here configuration means the position or the state of the bot at any given instant of time. So at any given instant of time, it is going to have three orientation. One is like three configuration, the X position, the Y position of the center of mass, and the direction in which it is aligned with respect to the X axis. So that together gives us the complete you say description of the current state of the robot in a 2D plane. When it goes to 3D, things are different. So we are talking only in the 2D plane. Now, input as in how are we gonna control our bot? So it is gonna be through a linear velocity in the direction in which it is pointed at that particular instant of time, that is theta t, and there'll be an angular velocity, okay, and everything is with respect to the right hand rule. So, like going forward from here, in the controls, what we do is to generalize our algorithms for every system. We derive it in terms of, or we talk in terms of V and omega, and we do not dive much into the model. So this is a differential bot. There'll be some VL and VR that will be the actual thing that you can control through your microcontroller, but there'll be an equation that can relate VL and VR to V and omega. So we'll talk in terms of V and omega. Okay. So while going through this particular algorithm, we'll assume that we have the position and orientation of the bot available. That is the state or configuration to say. Okay. Next is we can measure and control. As I told you that we'll be controlling linear speed and angular speed. So we'll assume that we are able to control it through our microcontroller. At the same time, we are able to measure it for being able to uh, like take it into a feedback loop. Okay. Next is we need to know about the obstacle that will come around us. So for that, we need a sensor skirt. Sensor skirt means a bunch of sensors mounted around your robot to sense obstacles or various different things. Okay. So this 1, 2, 3, 4, 5 I'll call as sensor skirt, which is sensing the obstacles. So with this, if anyone has any question, you can raise your hand quickly, or else I'll just proceed with the algorithm. Okay. Um, okay, so I guess I'm good to proceed with the algorithm. So we'll start with the algorithm. So with the algorithm, what you'll develop is that you can see like a path over here. So you should be able to derive one such for yourself. There'll be some defined goal over here or somewhere. Okay. So now the objective for our problem is to navigate our bot from a initial location to a defined final goal in an unknown environment. So unknown word is quite stressed over here because things are very different when you know the environment and when you don't know. So in a known environment, I can use various algorithms, A star or some other algorithms to actually take our bot from initial position to the final position on the best possible path. But when the environment is unknown, I do not know what I might encounter. So I do not really guarantee a best possible path. I just start towards the goal with some strategy that I'm going to discuss. So the strategy will be like it will go from a simplistic approach to a difficult approach to be able to generalize for every possible environment. Okay, so the simplistic approach will be that we'll assume that our environment is free of obstacles, as in there is only our bot and the final goal, and we do not have any obstacle in the environment. And then going further, we'll introduce obstacles, and obstacles also can be varied type, like it can be point obstacle for control strategy in a uh, like in a hypothetical world, we can have a point obstacle that is just coming at a point, and then actual obstacles are going to be concave or convex. By convex, I mean such obstacles that will have a flat surface kind of a thing, and concave I mean such things which often comes as a labyrinth or a maze kind of thing that can often confuse your bot. Okay. So going further, we'll develop algorithms for each of this. So for the first very simplistic map in which we do not have any obstacle, that is obstacle-free environment, we are gonna call it as goal-to-goal behavior. That is a go-to-goal, sorry. So I have an initial state from where I want to navigate to this as my goal point or the final state. Okay. So how do you achieve that? So this is my bot and this is the configuration of the bot. This arrow points the configuration, the initial configuration. So bot is at this X comma Y position in this orientation. So thing is very simple. I'll just try to turn in the direction of the goal and then proceed over there. So I change the direction of my bot such that it points towards the goal and then I keep proceeding straight towards my goal until I reach my goal point. Okay, so by this in a very simplistic environment, I have been able to navigate my bot to the final position. Okay, does anyone have any queries? You can raise your hand. Aryan, yes, we are like in Unicycle model, we are going with a differential bot. But as I told you, this algorithm can be generalized by taking it for V and omega. Okay, and yeah, Uh, in this particular blah, I'm gonna keep it very intuitive. I'm not gonna introduce any piece of code that is like PID tuning for taking your desired value to the actual value. So in this particular algorithm, we are gonna work on how do you actually find the desired value, as in whatever we are working on, that is gonna give you a desired path that you would have followed. But when it comes to the control algorithms, then you might have some other loops involved to take feedback and ensure that you're gonna going on your desired path. Okay, so this blah will cover a very intuitive feel of things like how in general you can do it. And then going further, we might have some mathematical basis that can come into subsequent. If interested, you can we can talk about that later. Okay, so we have been able to solve very first problem, that is in a obstacle-free environment. Now let's see when there is a very simple obstacle. I'll consider it as a simple obstacle or a point obstacle to say. Okay, so now as you say, had I gone straight, I might have bumped into this obstacle. So what do I do? So as soon as my sensor senses this obstacle, I have to do something so that I avoid it. So there is an option that I sensed an obstacle and I just start like run. I'll change my position to the direction exactly opposite to the obstacle and start proceeding in that direction. So this is called a very like hard switch, you can say. That is, I'm only focusing on avoiding obstacle, and whatever my goal point was, I have not taken that into consideration and given the utmost priority to avoiding obstacle. Okay, but this is not a very good approach that you find an obstacle and you just randomly starts going away from the obstacle. I won't say that it's the best thing to do in a situation when we have an obstacle. So we'll try to blend the behaviors, that is avoid obstacle and go to goal. So I'll call this behavior as a avoid obstacle and this as a go to goal. We'll try to blend these two using some values, like some ratios or something that you can work upon using your dimensions for the bot, and how exactly that will come into tuning of parameters. We'll not get into that. But yeah, we can blend the two behaviors such that we go in a direction such that we are avoiding obstacle as well as we are going trying to go towards the goal. Okay, so now I have instead of going in this direction, and I have effectively changed my direction to this particular path and avoided the obstacle at the same time going towards the goal. Okay, now once I have cleared my goal sufficiently, I'll switch back to my behavior in which I'm supposed to go towards the goal. Okay. So I have been using terms like behavior, switchback, and such things like that, and condition that I said after having ensured that I've gone sufficiently away from my obstacle. So, talking of it intuitively, things seem simple. Kia, you found an obstacle, you went away, you blended the option, and now you're after having gone away, you again started to proceed in the direction of obstacle. But thinking of it in the programming perspective, as in the language of computer, how will you make a computer understand the same? So this is a separate thing that it comes under hybrid system. So what a hybrid system is, it's like you have different behaviors for different point of time, and you switch between the behaviors as per the situation. Okay, now, every single behavior like Q and Q dash over here are behavior or mode of operations. So that means like, say here, I had two modes of operation. One was go to goal and another was avoid obstacle, right? So now they'll come as Q and Q dash. Now, what is a guard? A guard is a condition that tells the computer when to switch from one behavior to the other. So it's like I'm using goal to goal. I sensed the obstacle that had come into the region in which my bot is at risk or I wanted to go away. So say the distance from the obstacle has become less than some um epsilon. Okay, in that case, you want to switch to avoid obstacle behavior. So that is a condition that transitions from my avoid go to avoid obstacle. That is Q to Q dash in this case. Now, reset is not that usually used or not that intuitive. So still I try to give a feel of it. So say I'm switching from Q to Q dash, that is one behavior to other. So I have covered that at the beginning of the um, let's go to that. Okay. Yeah, over here I said I can use V and omega as my input, right? So V and omega is the input. I'll talk it in terms of state. So X, Y, and theta are state, and X dot is this. Like the first derivative of state is this. Now, as I told you that at the same time I could have been controlling my VL and VR. Okay, but we are trying to control it through V and omega. So this was to tell you that there is different possibility of input for the same system that we can have. So suppose I reset from one, like I go from one particular behavior to other. So situation might arise that I have to take a transition of my state. That is, for now I was controlling V and omega, but having to change from one behavior to other, I have to again go from V omega to VL and VR. It's like it's just an example. It's not in this case, but there might be a situation like that. So for that thing, we have reset. That is any abrupt change in the state that we need while transition is going on. So here the abrupt change was going from V omega to VL and VR. So in general, we want everything to be continuous, but while changing your behavior, things might be there might be an abrupt change. So to encounter that or handle that, we have this reset. Okay. So
Shubham,
this over, yeah,
just a second. There's a question.
okay, yeah, I'll take that.
Yeah,
Uh,
the thing is that I just wanted to know how you are controlling V and omega.
uh, okay, so V and omega can be controlled using different control theories. They can be approximated as a linear system, or you can control it as it is using a PID control. We'll not get into that as of now because
No, sorry to interrupt you.
yeah,
My
yeah.
question is on very layman language. What is the
Yeah.
mean of controlling V and omega? I mean, like, are you controlling the rotational velocity of the wheels in the board?
Yeah, yeah. So I'll answer that. So what I mean by controlling V and omega is that the entire algorithm, like whatever controller it has, it will give V and omega as the output. So suppose I'm running some algorithm inside, given some given some particular like information about the system. There is some algorithm which is computing certain things. So after computation, it will give me the linear velocity of the bot and the angular velocity of the bot. So that is what I mean by controlling V and omega. Does
Okay,
that
so
clear
what
your
is
answer?
actually the inputs inside the system? I mean, what is the input
So
in a
inside the
control?
system, like my controller will give the input as V and omega, but that V and omega has to be converted later into VL and VR. That will be done by some actuator. So there are different that I guess we'll talk about it a bit later because that will dive into a separate thing that will be about a control system. Okay, and in general, over here, I want to talk about navigation. So
Okay.
we'll take it up later. Okay, but yeah, a intuitive thing I would say is that my controller will give the output as V and omega. Okay, yeah. So um, I'm going ahead from here. So yeah, this diagram over here explains this general hybrid system. So you have certain behavior f1 of x, okay, and this starts from the state x0, okay. Now suppose a situation arises that this condition is satisfied, that is this particular condition g1 of 2 is a condition that if encountered will switch from this behavior 1 to behavior 2, and while switching we'll reset our states using this particular reset matrix r12. Okay, so by this, like say this is one condition in which I've switched from 1 to 2. Similarly, from 2, I can switch back to 1 given this condition, or I can switch back to 3 given this condition. We'll understand it more through certain like examples over here. So examples of hybrid system, let's talk about thermostat. So suppose thermostat's job is to to break out the circuit once a particular desired temperature is reached. Okay, so suppose the temperature has already reached the desired value. So if you want to, that means now I want to switch off my heater. So this particular function is uh, assume that the heater is on and over here the heater is off. These are two different behaviors. In this card, I'm sorry, let me. Am I audible? Anish, can you confirm?
Yeah, yeah.
Okay, thanks. Sorry for the interruption. Yeah. So this particular like switching from behavior 1 to 2 is done when the temperature at the desired coil is reached a little above the desired value. Okay, I'll cover the significance of why I want a little above and a little below the desired value. Because say if I exactly try to switch at the desired value, I'll switch here and immediately it will sense that the temperature is such that I need to switch back. So it will be in an infinite loop where it will keep on switching between the two behaviors. So that is why we have a epsilon over here to ensure that I do not infinitely go into a loop where I keep switching back and forth. So the guard is TD plus epsilon, where I switch from one particular heater on to heater off behavior. And when the temperature is below TD and some epsilon, I switch back to heater on. Okay, similarly, over here, there's a gear system. And the same is the significance of C1 and C1 prime being different because I do not want them to be same. Otherwise, I'll keep switching back and forth between these two. And that's called a separate thing called sliding mode that we can, if interested, you can read about it. Will not be covering it over here. So um, again, RPM, once your RPM has reached above a certain value, you switch up your gear. And again, if you want to go further, you switch up your gear. And if you want to go low, you switch down your gear. So this is another example. Now, talking it in our context, like whatever we have done so far. So over here, I was using my goal to goal behavior. That is, I was going straight, but I sensed that the safe distance from the obstacle is less than the desired. So I go to goal avoid obstacle behavior, and I keep avoiding the obstacle until I have made a further safe distance from that epsilon. Again, the significance of this epsilon is that I do not want to be switching back and forth between the two behaviors. Okay, so Hence, I was like, this is how my computer will deal with such situation. So there is one particular behavior that is goal to goal. I'm nicely going in the direction of my goal. And suppose at any instant of time, this particular condition is met, I'll switch from one particular behavior to another behavior, and then like I'll start going like start following this behavior until and unless I do not encounter this particular condition, that is I've made an extra of epsilon distance from the obstacle. And once that is done, I'll start following the again go to goal behavior, that is the blue line over here. Okay, one thing to note over here is that I do not have any reset condition R1, 2, or anything like that, because in this case, there is no abrupt change that is required in the state. Okay, so given this, until now we have talked about a very simple obstacle, okay, like this. But say the condition is something like that. This initial post says like this now my board is represented by this dot and this is the goal point. Okay, now suppose this is my board and I'm going towards the goal. What will happen in this case when the obstacle is something like that, a convex obstacle? So now we have increased the difficulty of the obstacle that we are supposed to encounter. So what is going to happen in this case? Will our bot be able to encounter this? Let's see. So you can see like the bot started to progress and having come at a T safe distance, it senses that no, I cannot go any further. I have to switch back to avoid obstacle. Like I have to start avoiding obstacle. So obstacle is this. This is the avoid obstacle distance. This is go to goal distance, and this is the blended behavior that the bot will follow. So the bot will start going in this direction. Now again, like having done, now it knows no, I have reached a safe distance. I can start following the goal. It will keep doing that. Now it will start following the goal. It will come here again, and there'll be a point like now again it will start following the goal. Again it will go away following the goal. There might be a point when the bot is perfectly in line with the goal. Go to goal behavior is here, and avoid obstacle is exactly 180 to the goal. So, like the motion that the bot did was quite zigzag kind of thing. Okay, it just kept on going like this. So this is not a desired behavior that will expect uh, to the bot to do. Or we should not be planning our bot to go in such a fashion. So one thing is sure that this is not a desired behavior, and we need modification. So, what modification can we do? And before we go to modify, let's see this scenario. Now, in this scenario, here's an obstacle, here's an obstacle. Like our bot will entirely be confused based on the current scheme where to go, and it will not have any, like, it doesn't know where to go and it cannot do anything. So, in such a scenario, what we'll do is we'll try to modify our algorithm to deal with such situation. So I mentioned about follow wall also in the write up. So we have seen go to goal and avoid obstacle behavior, but now comes following of wall. So what do we do in such a scenario is that once such obstacle is detected, instead of going to avoid it, we'll start to follow that particular thing. Okay, so and will avoid the obstacle only when we have reached a further distance into the obstacle. That will cover later that what to choose, follow wall or avoid obstacle in such a scenario. We'll try to cover it later through our diagram. But first, let's see about what follow wall. I'm sorry, what follow wall behavior is. Okay. Uh, am I going too fast? Do I need to slow down my pace? Uh, okay, nobody has an objection, so I'll go with this
Yeah,
pace.
it's going fine, man.
Yeah. So I want to follow the wall now. So what do I do? It's like following wall has two given direction. So again, I'm not gonna go into the control equation that will be involved in following wall. That will have its own loop. I mean feedback loop and all. But we are saying that I just want to follow the wall now. So I can follow it in clockwise direction or anti-clockwise direction. So in such a case, which one to choose, right? So here's an option, and obviously, given the information that I know, I can try to choose the better one, right? So which will be the better one for now? Obviously, the one which at this point of time is taking me closer to the goal. Okay, to analyze that, see the angle between clockwise direction and the go to goal behavior, and anti-clockwise and go to goal behavior. As like this angle being more than 90-degree is trying to take me away from goal. Otherwise, this angle being less than 90-degree is trying to take me towards the goal, right? So what we'll try to do is we'll try to go in the direction in which is taking us closer to the goal. That is the clockwise direction. So how do I identify that condition? So to identify that condition, we have this particular thing over here. The angle between clockwise and the go to goal behavior should be less than 90-degree. That is, the cos angle of that should be positive. Okay, that is what I've tried to mention over here. Okay, this will come as our guard condition. Okay, so in this, there's goal to goal and follow wall clockwise. If this angle is greater than zero, that is cos of this is greater than zero, that means uh, the angle is between 0 to 90-degree, and that is what we are supposed to follow. Okay, and if not, the if it's for anti-clockwise, we'll follow that. Okay, here CC represents counterclockwise, same as anti-clockwise. So over here, we know like out of the two option available, we need to go in clockwise direction. Okay. So we have now three behaviors. That is, we have go to goal, avoid obstacle, and follow wall. So I would like to like one of you to raise hand and speak. Like, do you think is it all sufficient, or do we need anything more? If anyone would like, yeah.
Uh, the length of the wall in the clockwise direction is larger than the anti-clockwise direction. It will be difficult, right? What if what if there is a closed wall in the clockwise direction?
Yeah, so as I told you beforehand, this is an unknown environment, and in an unknown environment, we do not know really what our world is. But at this particular given point of time, we have to make a choice. So the choice is the best with the given piece of information. That is what I tried to emphasize on, like to convey. Yeah. Like had the world been known to us, we would have been able to use some other algorithms to actually like take out which would be the best path. But as it's unknown, we have to choose the best from the given piece of information. Okay, so like I've given the answer to the question that have we done, it's no. And I've given a hint also over here that what is left. What is left is to like now I have entered. I'm sorry. Just give me a minute. Anish, can you confirm if I'm audible and if there is some noise?
Yeah, it's fine now.
Okay, cool. Sorry. So the thing is that suppose let me switch back to one of the diagram. Okay. Yeah, over here. So in this diagram, as you know that there is different guard condition if you enter from one behavior to other. There is a particular guard that tells you that you need to enter from one behavior to other. And then there is some other guard that tells you that you need to exit this behavior and enter into the other behavior. So we know the condition that we have to at which we'll need to follow our wall, but we don't know yet when do we exit from that behavior. So let's next try to answer that. So when do we exit? So to exit, we'll have two conditions. One is clear shot, and another is that we have progressed in the direction of goal. Okay. So what do I mean by clear shot? So at this point of time, if you can see, my avoid obstacle, that is that behavior will take me in this direction, whereas my goal to goal behavior will take me in this direction. And this particular angle is greater than 90 degree. And also you can see that there is no clear vision to the goal that I have at this particular instant of time. Okay, that means this is not a appropriate time to shift from my follow wall behavior to go to goal behavior. At the same, like if you want, you can analyze your bot to be at some other position, and you'll come up with the same conclusion that it's not the appropriate time to shift back. Okay, so even at this position, if I see, it won't be appropriate time because the avoid obstacle is in this direction, while my go to goal is in this direction, and I don't really have a less than 90 degree of angle over here. But say I've been following wall like this, and my bot has reached here. Okay, here or here somewhere. So at this point of time, my avoid obstacle behavior will be in this direction. Okay, and go to goal behavior will be in this direction. The angle between these two is less than 90 degree, and now you can see that I have a clear shot to the goal. Like really, I can know ki I have a direction in which clear shot means there is a direction in which I can go to the goal without having to encounter this obstacle. Okay, that is why we are using avoid obstacle of behavior of this and go to goal to check if I have actually encountered or cleared this obstacle and I can proceed in the direction of goal. Okay. So this was one of the condition. Now say my bot is over here. Okay. Now if the bot is here, avoid obstacle will be in this direction and go to goal will be in this direction. The cos angle is again less than 90 degree if you can take a feel of it. Okay. So again, should I at this point of time switch back from follow wall to go to goal behavior? I guess no, this is not the right time. We'll start going in this direction and we won't have achieved what we desired to. So, along with this clear shot condition, there is another condition that is progress. So, progress is from the instant that I started following the wall. Suppose I started following the wall from here. So, there is a particular distance from here to here, that is xg. I'll take the distance from the goal at the time I started following the wall. Now, I'll keep a check of that. Okay, at any point of time when I have a clear shot and I have moved in the distance of towards the goal from from the time I started started following my wall. Okay, so this is what it means progress. That means at this point of time, the distance from the goal is less than when I actually started following the wall from here. So these two conditions together tell me that it is the right time to switch from follow wall behavior to go to goal behavior. And I can have successfully tackled this particular obstacle and I'm good to go in the direction of goal. Okay. So any questions on that? Okay. Given no, let's analyze this complete diagram. This pretty much summarizes all that I've discussed so far. Okay, so we'll spend a good amount of time discussing this particular diagram. And if any one of you have doubt, you can raise your hand, and Anish will ask me to answer your question. Okay, so say I have entered my like this is the state at this is the point at which I uh, start in the unknown world, and this is the state at which I would have reached my goal position. Okay, so I start with go to goal behavior. Okay, and in go to goal behavior, I just follow go to goal behavior until and unless either of these two conditions is met. That is, I'm close enough to an obstacle, I'll start following the wall in counterclockwise or clockwise direction based on the angle. Wherever it is less than 90 degree, that is between 0 to 90, I'll start following the wall in that particular direction. Okay, now suppose it was clockwise as in the example. So I started following the wall in clockwise direction. And over here you can see a reset condition. So this like here there is a reset condition because we are storing something while switching from this behavior to this behavior. As I told you in this condition that I need to store the distance from the time I started following the wall to the goal. Okay. So that is x minus xg, that is the d tau distance at the time I started following the wall has been stored. Okay, now I'm following the wall in counterclockwise direction. Say that by some due to some error happened due to some disturbance, and I by chance went too close to my obstacle. Okay, so if the bot is too close to the obstacle, that is less than delta distance, I'll start following the avoid obstacle behavior. Okay, and I'm with the avoid obstacle behavior either till the time I have cleared that obstacle sufficiently, and in which direction at that, like after I have cleared my obstacle. So this particular condition can happen at multiple instants of time. So one say key no, it happened with because of a disturbance in my system. Other can be when, like say, another obstacle came while following the wall in that particular direction. So there can be a situation that I'll have to now follow the wall in counterclockwise or clockwise direction. Again, we'll see that by checking this particular condition. And this delta thing is obviously that we have cleared the obstacle and we can start following back my wall. So say this time I went to the counterclockwise direction because of this condition. Now, again, like you can see, after while I try to enter, have this as my reset condition. So I'm storing the distance towards the like distance that I'm away from the goal at the point I try to enter this behavior. Okay. Now, when do I go back from this to again go to goal behavior? So this is the condition over here that we'll need to have. This condition specified that we have progressed in the direction of goal. That is at the point of time when I entered following the wall, I had d tau distance, but now I know that my distance is less than d tau, and at the same time I have a clear shot. That is this condition that I can view my goal, avoid obstacle, and goal is has an angle of less than 90 degree. I have a clear shot to the goal and I can go in that particular direction. So now I'll just start switch back to my go to goal behavior, and I'll start traversing towards my goal, and yippee, we have reached our goal. Okay. So yeah, pretty much this. So we have been like able to navigate our bot in an unknown environment. Okay. So let's say over here. Okay, so there was some go to goal behavior. The goal might have been here. I was just trying to follow the goal, and then I had to switch back to follow wall. I started following the wall. Again, I have a clear vision to the goal. I started following the goal. Okay, and I have progressed in the direction of the goal as well as a clear shot to the goal. So I started back to goal behavior, and this is a very like. Basic thing that we have that we can do to follow a given like to solve a navigation problem in an unknown environment. Now if anybody has any question, I'd like him or her to raise that. This is pretty much that I wanted to deliver on this particular blah topic.
I'm just confused with these notations. Uh,
Yeah.
like this UGTG, comma UFWCC. Uh, can you just explain that?
Okay, so wherever you see this term GTG, that means go to goal. At the same time, AO means avoid obstacle. U means a behavior. Like
Mm-hmm.
what basically in controls we use U to specify our input. Okay, so that is like input is following this particular behavior, that is go to goal. At the same time over here, input is following the behavior follow obstacle, follow wall in the counterclockwise direction. So that is meant by these particular UGTG or U follow wall conditions. And what I mean over here is that this particular thing, you goal to goal has a direction that, as I've been able to have been showing you through those arrow marks. Okay.
Hmm.
So over here you can see you goal to goal behavior has a direction. Okay. And at the same time, my you avoid obstacle thing also has a direction. Okay. So that is what I'm trying to do over there.
Okay.
You avoid obstacle. Um, this in this case, I have like say clockwise direction has a direction that is this, and goal has a direction that is this. Now I'm trying to take a cos angle between these two because I need to have conditions in computer's language. Okay, so the condition in computer language could be very simple. Take the cos between these two angle, that is dot product. It's really easy to take. And if my dot product is positive, that means I need to follow this direction. If the dot product is negative, I dot product of this is negative, that means I need to follow this direction, right?
Okay.
Like that entire dot product thing is a very simplistic way of choosing, like seeing the angle condition being greater than or less than 90 degree. Yeah.
Just to calculate the orientation difference.
Yeah.
And this modulus x minus xg, this one in the center.
Yeah, x minus xc. So let's say x is my position of the bot with some. Let me quickly draw some lines over here. Now this is assume this has to be your coordinate axis, okay? And there is some 2 points, okay? One is this point, and another point is over here, okay? This point. Let me remove this picture for a quick second so that we have a better feel. Yeah. So suppose this is the current position of my bot, like the position at time t, and this is the goal that I want to reach. And I'm measuring both the position with respect to this coordinate system. So this will be the x and this will be xg. So modulus of x minus xg will give me the distance from the current position of the bot to the goal position. Okay, so I'll measure this distance now. uh, the gist of this was I want to know that what is the distance from the goal of my bot at the time I'm starting to follow wall, so that while trying to exit from that condition, I'll check that whether I have moved in the direction of wall or not, in the direction of goal or not. What is the need of that? Again, I'll try to specify that. Suppose over here at this particular time, okay. Mm. Let me quickly show you that over here. Okay. Okay, yeah. So at this particular point of time, if you see, my avoid obstacle direction will be exactly opposite, right? It will be somewhat this direction, and go to goal behavior is in this direction. Again, my angle is less than 90 degree, but that doesn't mean that this is the appropriate time to shift from this follow all behavior to go to goal behavior, because I started following from here and I further moved away from my goal in order to clear this obstacle. That means uh, I need to go further, follow this wall until I've moved closer to the goal from the time I started following the wall. Does that make sense?
Yeah.
Okay.
And the dr, actually you are referring to some dr. What is the meaning of dr? It's a
Let me.
distance.
Yeah. D tau is just a notation I've used to uh, detect the
Quantify this
distance.
distance.
Yeah.
Okay. Okay. Thank you.
Yeah, that was a good question. Anybody else has any question? Okay, we'll wait for a minute. Yeah. Till you think about that. So in this pla we just covered about like a basic intuitive way of how you can navigate your bot in an unknown environment. We have not covered any fancy control algorithm that will implement the same. So to do that, there'll be again separate. There'll be piece of codes. There'll be mathematical formulas that you'll have to derive and all. So we have tried to skip all that because it's not that it will take some time to follow that, and maybe we'll try to supply some of those along with the in after the session we'll try to put that if possible, give some material on that. I mean, okay, as I see nobody has any question, then well, thanks all for attending the session, and I hope that you all got the gist of what I actually wanted to give in this plus session.